actually write the steps down in a problem like this because it's pretty complicated and the steps are important. So the first thing I'm going to do here is draw the free body diagram of each object first, though, without friction. And here's why. Honestly, we don't know which way friction points on block A. It's not immediately clear whether block A has a tendency to be pulled up or slide down the incline. So let's do that. Block A has a force of gravity acting on it and has a normal force acting on it. It has a tension force acting on it. And like I said, it has friction. I'm going to skip that for now because we're not sure whether it's going to be having a tendency to slide up or down. I do want to tilt the axis. Force of gravity and the y-axis have the same angle as the tilt angle, and that's 30 degrees in this problem. This block A has a mass of 25 kilograms. So 25 times 9.8 is going to give us its weight, which is 245 newtons. I always want to find the x and y components of a force that's at an angle. Since this is adjacent here, the y component is going to be 245 times the cosine of 30, and the x component in there is going to be 245 times the sine of 30. So let me take a moment to calculate those values. Okay, so we have 212.2 for the y component and 122.5 for the x component. So without friction, that is the complete diagram for the block that's on the incline. The block that is hanging is much easier to deal with. That just has its force of gravity, which is 10 times 9.8, or 98 newtons, and the tension force. Remember, in a pulley problem, these two items are connected. And so here comes really our next step. We want to find out which way does this have a tendency to move. And so we are going to compare the total force parallel to the string. Those are the only forces that determine whether or not the string accelerates. So compare the total force parallel to the string in each direction. Now, this is a relatively simple problem. So here, remember that the tensions will cancel one another out. So I'm not going to worry about them. But here, pointing this way, maybe I'll draw it over here in that direction, but pointing this way, we have a 98 Newton force. And if I follow the string along over here, we have the x component of gravity, which is 122.5 newtons, pulling that way. Those are the only two forces that are parallel to the string other than the tension forces that cancel out. And so now, looking at this, we can see that the pulls on the string in either direction are not balanced. And we can figure out which way friction has to point if it's going to balance things out. Friction, if it's going to balance things out, has to give some help to this direction over here. So friction would point that way. Friction has a tendency to point that way because the entire system has a tendency to slide to the left. So maybe we'll just write down here that friction will point in the opposite direction of the larger total force. The other thing that we can do, step 4, is we can figure out, okay, so how big does friction need to be to keep things at rest? Hopefully that's fairly obvious that to keep things at rest, friction has to make up the difference here, right? So there's 122.5 newtons pulling this way, and there's 98 newtons pulling that way. And so the only way this thing is going to stay at rest is if friction makes up the difference of 24.5 newtons. So step 4 is determine the difference between the forces from above meaning from this step right here, and that is how big friction must be to keep the system at rest. Now, we are not done because maybe friction can't be that big. Remember, we're dealing with static friction here. Static friction has a maximum possible value, and it's possible that the maximum possible value of static friction can't handle as much as 24.5 newtons. So that's our next step. Our next step is to determine the maximum possible static friction force. So determine Fs max, we'll call it. So we have a formula for that. Fs max is equal to the coefficient of static friction times normal force. The coefficient of friction was given here for static friction as 0.65, but now we have to figure out the normal force. Let's go back and look at our picture. So the normal force occurs in the y direction over here, and maybe you can immediately see that the normal force and the y component of gravity are the only forces in the y direction. And there's no acceleration in the y direction. That's why we tilted the axis so that there's no acceleration in the y direction. So these two forces have to be balanced. Normal force must be equal to 212.2 newtons. If you like equations, let's look at it this way. Acceleration in the y direction equals net force in the y direction divided by mass. There is no acceleration in the y direction. It's not accelerating on or off the incline. The forces in the y direction are positive Fn, negative 212.2 divided by the mass. That doesn't even matter because when you multiply it over to the other side, you would just get 0. So in the end, we do get Fn equals 212.2 newtons. So that's our normal force, 212.2 newtons. And so we're seeing that maximum static friction is 65%, 0.65 of 212.5. That is 138.125. So the maximum force that static friction can handle is 138.125 newtons. We determined earlier that it only needs to be 24.5 newtons. So we can conclude here that this object definitely stays at rest and that static friction is equal to 24.5 newtons. Let me just go one step further because it's a good example. Let's say that we had found out that static friction is not strong enough. So in other words, we find out that the system is sliding. Let's see if we can figure out the acceleration of the sliding system if it does move. So first of all, which way does it have a tendency to slide? Well, we determined earlier that if it does slide, it's going to slide this way. It's going to slide down the incline. So if it's sliding down the incline, that means that friction, and now if it's sliding, it's kinetic friction. Kinetic friction is going to point up the incline. So we're going to have to calculate how big kinetic friction is. So kinetic friction is equal to the coefficient of kinetic friction times normal force. Kinetic friction coefficient from the other page is 0.42. Normal force is still 212.2. So 42% of 212.2 is 89.124. 89.124 newtons. So now we want to figure out the acceleration in the x direction. So we'll just use our good old Newton's second law equation. I'm going to add up the forces that are in my diagram in the x direction from the previous page. Let's look at that again. We're talking about the forces on this one right here. Actually, we need to add up the forces on all of them put together because they are linked together and they're moving as a system. So that means we have the x component of gravity, which is 122.5. We have the kinetic friction force. We have this tension force. We have this tension force. And we have the force of gravity. We have to put all of those forces together. Also, since it's a pulley problem, we have to make a decision of which way we want to call the positive direction. I usually like to make that the direction that I know it's going to move. And we know it's going to move this way. So anything that points that way, I'm going to make positive. So let's put that into my equation. That means I have the x component of gravity at positive 122.5. I have kinetic friction pointing the other way at negative 89.124. I have a tension force on the one that's on the incline of negative Ft. I have a tension force on the hanging one that's positive Ft. And finally, I have a gravity force on the hanging one of 98. Those are all of the forces on both objects in the system, all added together, which means I have to add their masses together, which would be 25 plus 10. And so let's see what we get here. Of course, this is why we add both objects' forces together, because the internal forces, the tension forces, cancel out. And so I get a total of 122.5 minus 89.124 minus 98. And so the net force, this is interesting, but not crazy. The net force is negative 64.624. Interesting, I say, because it's negative, divided by 35. And so when I divide that, I get negative 1.8464 meters per second squared. So what does that negative sign mean in the context here? It means that the acceleration, if this thing does slide down the incline, which I'm calling the positive direction, the acceleration is actually going to be up the incline, which simply means it would slow down. If something makes this thing slide down the incline, what's going to happen is it's going to slow down and then obviously come to a stop.